Let's continue working on number 2 on page 10 of your 8.3 notes. So we're practicing graphing I'm going to try to make this a little bit lighter. Graphing an exponential function. We talked about that because this is with the x, it's going to be the opposite of what's happening because positive 1's usually right, but x is left or right movement. So we do the opposite, which means this is the mother function shifted left 1 unit. We put in our standard table, -2 to 2, but when we went to plug in 2, it was going to be 3 to the third, 2 plus 1, which is 27, which is off the graph. So then I went on the other end and thought, okay, I'll add 1 to that. So our new x is -3 instead of 2, so that looks like 3 to the -3 plus 1, which is 3 to the -2. Who remembers what that is? Flip the base 1/3, and then the exponent becomes positive. So 1/9. Okay, this graph has not been moved up or down because there's no number outside, so that means I can assume that the horizontal asymptote stays at y equals 0. And put that in as it's a graphing guide. It's just like, remember when we did the axis of symmetry with the parabolas? We dotted it because it wasn't part of the graph, but it was a graphing guide, so we could like reflect points across it. This is a graphing guide in that it steers us and says, don't touch me. You can get really, really close, but don't touch or cross me. So it helps me to draw the graph. So -2 and 1/3. So that is going to be -2 and 1/3 is just barely going to be above the x-axis. And then -1 goes with 1, 0 goes with 3, 1 goes with 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. These are kind of numbered weird. And then we had -3 1/9, which is even closer to 0, but still I'm just barely on top of that pink line. So then when we go to draw it, well, I do it in 2 things. So I draw this way, put arrows to show that it goes on forever. Then I turn it back around and do this and just skim right along the top of that pink asymptote without touching or crossing it. Just make sure you don't curl it up. I see students like curl it back up. It just keeps getting closer and closer and closer to that asymptote, but it never touches it, never crosses it. So just slide right along. And you can see why it's called exponential growth. It starts out really, really slow and then boom, shoots up fast. Make sure you put arrows on because on the final I do ask for domain and range. So let's go ahead and answer that. So domain, left forever, right forever, right? Remember on the page previous it said the domain is always going to go left and right forever because of the arrows. The range, so we slide our pencil so it gets close to 0, but it never touches 0. So that's why we have to use a parenthesis to show that it's not equal to 0. A bracket shows it is equal to 0. A parenthesis shows it is not. And then rolling our pencil, boom, up forever. So that will be infinity. And that's what I ask you to do on the final exam. Make a table, draw the graph, include the asymptote, name the domain and range. Okay, so that's what you'll see on the final exam. I don't know which one I put, whether I put a whole number base or fractional base, but you'll see the fractional base is just as easy as the whole number base to do. But remember how when it's a fraction, less than 1, it's going to be a decreasing function, where this base was greater than 1, so it's an increasing function. So let's write that just to practice our vocab. So this is an increasing function because from left to right, like we read a book, it is rising. So increasing function. Okay, ready to try a fractional base? And remember, we already know what it's going to look like. It's a decreasing function, so it's going to look like this. And there's no shifting, nothing added to the x, nothing added out here, so it's just a mother function with a base of 1/4. Okay, so let's go ahead and fill out our table. Like I said, I always start with the basic table, and then later if I see it doesn't work, then I replace it. So first we're going to have 1/4 to the -2, and I like to just write them all out first, then I don't have to keep looking up there. 1/4 to the -1, so this is just going in place of all the x's. 1/4 to the 0, 1/4 to the first, 1/4 to the second. Okay, so here's some more chapter 4 stuff. When we have a negative exponent, we put the base under 1, but if the base is already a fraction, we learned you just reciprocate it. So to make that exponent positive, the reciprocal of 1/4 is 4, so this is really just 4 squared, 16. And 1/4 to the -1, to make the exponent positive, we reciprocate the base, so that's just 4 to the first, 4. Anything to the 0th is 1. Anything to the first is itself. And 1/4 times 1/4 would be 1/16. 1 times 1 is 1. 4 times 4 is 16, which is a teeny tiny little number. So as we go to draw the graph, 10, should we add some points up here? 11, 12, 13, 14, 15, 16. So -2 goes with 16. So since there were just a few points to add, I didn't mind adding those in. The other one, though, that was going to be 27. That's a little too much to add in. So -2, 16, -1 goes with 4. 1, 2, 3, 4. 0 goes with 1. 1 goes with a 4th, which is just a little bit above 0. And 2 goes with a 16th, which is even closer to 0. So before we draw, let's go ahead and put in our horizontal asymptote. We're not going to get to log graphing, but you'll see on log graphing, it's the inverse of the exponential, and it has a vertical asymptote. Remember how x and y are switched around with inverse? So if y equals 0 is the asymptote of the exponential function, x equals 0, which is a vertical line, is the asymptote of the log function. But you'll learn more about that in the next class. I just wish we would have had a little bit more time so I could have introduced you to some of the stuff. I think a lot of students are just going to have to work a little bit harder next semester to get caught up on what we missed out on. Okay, so there is the exponential function. I just made it crawl right along the asymptote. And does everybody agree the domain goes left forever, right forever, right? And is it going to be the same range, 0 to infinity? Roll your pencil. Yep, 0, but not included, to infinity. Here we go. Okay, so the rest of the section is showing you applications that to show you how exponential functions are used in the real world. So population is one of those. I know on my paper pencil test, I had a population problem for this section just because it's a very common use of exponential functions. So let's see how that looks. So f of x equals 76.3 times 5.012 to the x. So yes, it's an exponential function. Models the population of Soldavia in millions. So that's pretty important. So when you get an answer, you have to know that you have to add 6 zeros because it's in millions. And this is another thing that's huge. X years after 1996. So if it's 1998, X will be 2 because that's 2 years after 1996. If it's the year 2000, X will be 4 because that's 4 years after 1996. So just so you understand what that verbiage means. Without using a calculator, find Soldavia's population in 1996. And you will have tests without calculators in the next class. So good practice. So 1996, how many years is that after 1996? Trick question. It's 0 years after 1996, so this means x is 0. Because x is always how many years is it after 1996? Well, this is in 1996, so x is 0. So I rewrite my equation with all the x's filled out as 0. So the function value for 1996 is 76.3, parentheses 5.012 to the 0th power. And you may be thinking, oh my gosh, I can't do this. This is, too big a numbers. Not really, because anything to the 0th is 1. So this is really 76.3 times 1, because all of this turns to 1. We learned in chapter 4, which is 76.3. But remember, F is the population, and the population is in millions. So to get this answer correct on Connect, you have to write million people. So if you just write 76.3 people, you're going to get it wrong because it tells you right there, it says millions. So it's 76.3 million people in the year 1996. So you have to read the directions carefully to understand what X is, why we pick 0, because 1996 is 0 years after, and then to know to add millions to your answer, because it's not just 76 people in the country, it's 76.3 million people. Find Soldavia's population to the nearest million. So this one's asking us to go to the nearest million in the year 2000. So what would X be for this one? How many years is 2000 after 1996? 4 years, right? So this one we do get to use a calculator for. So this says go into the original function. Everywhere you see X, replace it with 4. So f of 4 equals 76.3 times 5.012 to the 4th. And then they want it rounded to the nearest whole number, because that would be million, right? Because this is in millions. So if this said nearest million, we'd write 76 million, because that 0.3 doesn't change it. So now let's type it in the calculator. So 76.3, oops, not 0.6, Norris, 0.3, parentheses 5.012, close to the 4th. And let's just make sure that looks good. Yep. Okay. And so this is the millions place because it's in millions. So 6 followed by a 9 says make it 7. So it'd be 48,147. And then we cut that off because it says nearest whole number, millions, because this is millions. And then we write million people. And we'll do part C on the next video.